So a couple of topographic profiles cutting across a rift. If we look at two different rifts, we can see they look really different, at least at first glance. But there are definite similarities. In this upper picture, we see, okay, here we're moving from the west coast to the ocean. We have a coastal range of mountains and then a basin. Okay. And we have the Sierra Nevada mountains. Okay, we know that's not part of a rift system. That was tectonic uplift from compression and different type of activity. But then we have this basin and range province. It's a low area between the Sierra Nevadas and this Wasatch Mountain range. Within that basin and range province, we have highs and lows. It's how it gets the name, basin and range. And then, but we can see that overall it's still lower than the mountains on either side. If we come down and we look over in the Middle East and we look at the Red Sea, so we have Arabia on the east-northeast side, and we have the Red Sea Hills on the west-southwest side, and the Red Sea between them, we have ridges on either side of the Red Sea. So the land is rising right up until it gets to the big basin, which is now so low and deep that it's been filled with a sea. If the basin and range province in the United States had continued to rift or, reactivates for millions of years, we'll never see it, but we could end up with something like the Red Sea, just on a very large scale, because the basin and range province is much wider than the Red Sea. On the other hand, we can have what at first glance seems like very strange uplift. So we've already seen how we can have anticlines and synclines in this extensional regime. We can also have uplift in this extensional regime. So we can get things like this small mountain poking up out of the ocean without having any compression whatsoever, but because of extension. This is an example along the coast of South America, along the passive margin, so no compression. West coast of South America has compression. That's where there's subduction going on and the Andes are forming. The east coast of South America is a passive margin. It's far from the actual mid-ocean ridge, but it is an old extensional area. It is the old edge of the rift. The crust is thinned, therefore it's weaker, and if there is buoyant rock underneath, magma plume, mantle plume, or even just an old deposit of granitic rock in a surrounding area of basaltic rock, that granitic rock is much less dense. Therefore it's buoyant. If the crust is thinned and weakened enough, the buoyant rock can actually rise. It's like the textbook gives the example of a balloon. If you have a big piece of plywood sitting in the water, you can have a balloon under that plywood, no problem. And the balloon is stuck there. It's pushed down despite its buoyancy. The plywood's not flexing, the plywood's not letting anything rise up, so that buoyant object is just stuck being submerged. However, if you take and you replace that plywood with something much more flexible, to represent the thinned, weakened crust, like, say, a sheet of plastic or a big foam rubber mat that can flex, and you set that over the balloon, the area where the balloon is going to be a bulge. It's going to be uplifted. That's the kind of thing we see here. Now, it didn't just pop through the surface abruptly. There was slow uplift as it flexed the weakened crust. Then erosion was happening at the same time, and the more durable parts of the rock are still there. The less durable parts of the rock have eroded away, leaving these really cool formations that are basically giant chunks of granite sticking out of the ocean. So what kind of tectonics are we seeing at the mid-ocean ridges? You can see all of these jagged lines are the mid-ocean ridges. We have extensional areas, we have accommodation transform faults, and then the next extension, and the next accommodation transform fault, and so forth. They are different than these other plate boundaries which are showed by the dashed lines. These dashed lines are either transform boundaries or subduction zones. These ridges can move at different speeds, so different spreading speeds. So we're talking about how fast, like, the east side is moving away from the west side, or the north and the south, depending on the orientation of the ridge. If they're spreading slowly, that a slow one refers to anything moving less than 4 centimeters a year. In human speeds and scales, even the fast one seems absurdly slow, but these represent whole continents moving at this speed. So this kind of stuff is pretty substantial. Even a slow one suggests that, North America is moving away from Europe at 4 centimeters a year. A fast one indicates North America moving away from Europe at 8 centimeters a year or more. That's a lot of stuff moving. I mean, the lithosphere, many kilometers thick, even in the ocean, thicker under the continents. All of that, from the mid-Atlantic ridge all the way to the west coast of North America, is moving away from all of Europe, all the way from the mid-Atlantic ridge westward. They're spreading apart. They're moving away from each other at multiple centimeters a year. It's a huge amount of force. That's why we get earthquakes. All of that force. There can be specific areas that bind, and there's friction and there's flexing, and then finally they release. Think of it like one of those wheels you see like on game shows and stuff, and it has little tines along the edge of the wheel, and there's a little flapper, and when the wheel gets really, really slow, that flapper sits there and it starts slowly flexing as the wheel moves a little more and a little more and a little more until it slips, and it slips very abruptly. That's like the area with an earthquake. As things are moving, there's an area where it's sticking and sticking like the little flag stuck on the edge of the wheel until it finally releases, and then it snaps back to where it's straight again. So anyways, we've got the slow, intermediate, and fast speeds of spreading. And the ridges are going to look different depending on what speed they're spreading. A slow ridge, or a slow spread, is going to give us ridges that are narrow. By narrow, we mean couple hundred kilometers wide. So that's still, that's like the size of a state for width, or more than one state. But comparatively, it's narrow. And it's going to have a deep trough at the center. So, we saw a trough in our cross-section drawings. That will be visible if you have slow spreading. On the other hand, if we have a fast ridge, a fast spreading center, there won't be a trough anymore. And the ridge is going to be very broad, 1,500 kilometers or so. Much, much wider ridge than in the slow spreading center. Now we think about, okay, so why is a slow one narrow and a fast one wide? Well, one of the really key things that they used to figure out plate tectonics and seafloor spreading were those magnetic ridges, or magnetic stripes in the ocean floor, and looking at the age as you move away from the ridge, and the thicknesses of those magnetic anomalies and how they were the same on either side. But the width of those is partially due to speed of ridge spread, and then of course also largely due to the duration of the magnetic reversals. But while they were doing that, they were finding that as you get away from the ridge to older seafloor, it's deeper. You say, okay, why is that? Well, if it's older, it's cooled more. If it's cooled more, it's denser, therefore it rides lower. It's like having a piece of dense wood next to a piece of less dense wood. Like if you have a piece of oak and a piece of pine, even if they're the same size, you float them in water, that pine rides higher. It's less dense. So as we move away from the ridge, the older rock is less dense. The older rock is more dense because it's cooled, and it sinks lower. At the ridge, it's still very hot. It's less dense. In a slow spreading center, it may only take 10 million years to move 100 kilometers. Actually, I could figure out exactly how much, 4 centimeters a year, so 25 years to go a meter. $25,000 years to move a kilometer. So after 25,000 years, it's moved 1 kilometer. It's had 25,000 years of cooling. 1 kilometer away, looking at a ridge that's, say 100 kilometers wide. 25,000 years times 50, 225,000 years before it reaches the edge of that ridge. It's now cooled enough to sink enough that it's no longer part of the ridge. On the fast spreading one, spreading 8 centimeters a year or maybe more, it's going to go at least twice as far before it cools the same amount. That means that ridge is much wider because the rock has traveled further, it has spread more before it cooled enough to sink. So here's a fast spreading ridge. We've got the rock moving out from the center, the magma chamber here. The buoyancy of this magma chamber is going to push this center upward as things are thinning. You can see that The magma chamber is due to the partial melting in the asthenosphere as the pressure is released as it rises, and then it comes out of the vent along the center of the ocean ridge, and it spreads away side to side, all these vertical lines showing you what used to be the edge of the magma vent. So all of these sheet dikes topped by pillow basalt, and then as you get away from the ridge, topped in sediment. So this is the basic cross-section of the fast-spreading ridge. You can see here how the slow-spreading ridge has a more curved slope and reaches a low area much closer to the center than this fast-spreading ridge. The fast-spreading ridge has more straight sides, and they stay elevated much further away from the ridge axis. So this fast-spreading ridge, no trough in the middle, just a peak slowly moving away with inconsistencies. It's not a straight line like up in the little dashed cartoon. These are actual cross sections, but no trough in the center at all. An intermediate one is a bit more level, and then for the slow spreading center, the edges of the ridge are on either side of a trough. So in the very center of the slow-moving one is a low area, a trough due to collapse. In the fast-moving one, it doesn't have time to collapse. So, taking another look, we've got a block diagram here. Here's the rising basalt flooding out. And you can see it's not all the way across, which we'll see again shortly. And this is our trough area, also called an axial graben. Faults towards the middle, coming towards each other on either side of it, so it's a graben. This is a volcanic mound in the center of the graben from the basalt pouring out and cooling. And on either side we have the faulting, and we have scarps where the edge of the fault block is exposed and collapsing. Now looking straight down on it, these gray areas are basically these volcanic mounds, and these white blobs are old ones that have been split apart and moved away from each other. And you can see like the gray is the current, here's 20 million years old and 20 million years old, 100 million, 150, 190, and so forth. The number is how many millions of years old it is, or actually thousands of years. I'm sorry, these aren't in millions, thousands of years old. So you can see that at no time is it a continuous release of magma along the whole rift. It's always in specific areas. So the spreading is uneven. The magma release is uneven. Zones of accommodation have to be present all the time. We're stretching something over a spherical surface. It doesn't split nice and perfect.